Recording. Okay, let's start our seminar on the next One World ABC seminar. Our speaker today is Irene Jubikanec from Linz. She will talk about spectral density-based and measure-preserving ABC for stochastic differential equations, and it is a joint work with Massi and with Evelyn Bakwa, also from Linz. So, Irene, please go ahead.
Thanks a lot. Can you hear me well? Everything is fine?
Yes.
Yes, perfect. Okay, then first of all, I'd like to thank every one of you for being here today and for being interested in our work. And I'd also like to thank the organizers for giving me the possibility to be part of this series of wonderful talks around ABC. Before I get to the topic, let me say a few words about myself and about the motivation behind the work that I'm presenting today. So I'm a PhD student in her final phase, working at the Institute for Stochastics at the Johannes Kepler University in Linz in Austria. And the work that I'm presenting today is a joint work with my supervisors, Evelyn Bakwa and Massimiliano Tamburino. And well, Evelyn is an expert on numerical analysis for stochastic differential equations, and Massimiliano, he is working on statistical inference for stochastic processes. And the feeling that we had, or that we still have, is that both topics, numerics and statistics, sometimes can strongly depend on each other, but often they are treated as very separate issues. So the idea of this work is to illustrate that when you perform statistical inference, in this case simulation-based inference via ABC, that it can be very important or very helpful or even necessary to use a numerical method to simulate your data, which is able to reproduce the correct structure and properties of the model. And that sometimes it can be a very bad choice to use standard methods such as Euler-Maruyama for SDEs. Okay, so the resulting article, the work I'm presenting today, it appeared in Statistics and Computing, and it is available open access under the link that you can see on the slide. So in case I succeed in arousing your interest in the following minutes, feel free to have a look at it for further details. Okay, so but now let's get to the topic, and let me introduce our setting of interest. So we are interested in statistical inference for multidimensional stochastic differential equations. We assume to have a setting which is well defined, to have drift and diffusion coefficients, which fulfill everything that is needed for having the existence and uniqueness of a solution process that we call X. And then we look at the challenging situation where this n-dimensional process can be only observed through a one-dimensional process that we call the output process. And this process is obtained as a function of the coordinates of X. So for example, quite often you may have a two-dimensional equation where one of the components models the observable phenomenon and the other one is just an assisting component. And in this case, the function g would just be a mapping of X to its observable coordinate. Or another situation, and I will give you a concrete example for that in a minute, is you might not be able to observe any of the components directly, but probably just a linear combination of some of the components. Okay, and in addition, we assume that this output process admits an invariant distribution. Basically, it means no matter where the process starts, it will go down, it will converge to some invariant regime, to some stationary limiting behavior as it is illustrated on this figure. And usually the output process will inherit this property by means of the marginal distributions of the process X. Okay, and what do we want to do? So our goal is to infer the parameters theta of the SDE based on discrete time observations of the output process. And we will do this by applying the ABC approach. And we want to make use of the underlying property that there is some invariant distribution. Okay, so to make this setting even more clear, I will introduce a concrete example, which is the one that actually motivated the work that I'm presenting today. It is the so-called stochastic Janssen-Ritt neural mass model. It's a model applied in neuroscience, and it is of so-called Hamiltonian type. So everything I'm presenting today also holds for similar equations of such type. Hamiltonian equations, they usually model some type of oscillatory behavior. Okay, but in particular, this neural mass model, it describes brain activity of an entire group of neurons in the brains of an entire region in the brain, and it describes EEG data. It stands for electroencephalography, and it can be measured by putting electrodes on your scalp. So for example, here you can see such an EEG recording. In this case, it shows algorithmic behavior, which has a frequency of around 10 Hertz, and it can be measured when you are in a very relaxed state, having your eyes closed. And this type of data can be reproduced by the output process of the model. So while the model itself has 6 dimensions, what can be observed is only the difference between 2 of the components. And this is what can be measured with EEG recording techniques. Then also it has been shown that this model admits an invariant distribution, so it nicely fits into our setting of interest. And there are 3 parameters we are mainly interested in. One is the parameter C. It's an internal coupling parameter that controls to which kind of extent the neurons are interacting with each other. And then there are mu and sigma, which can be interpreted as deterministic and stochastic external input coming from neighboring or also from more distant cortical columns. Okay, and what we wish to do is to infer these 3 parameters, to infer theta based on such EEG data. Okay, and we will do this by applying the ABC approach. And before I show you a very basic ABC algorithm that we used in this work, I just very briefly want to introduce some notation. So in the following, we denote with Y observed reference data corresponding to observations of the output process. Then we have Y theta stands for simulated synthetic data corresponding to paths of the output process. Pi theta is the prior, pi theta given by the posterior that we wish to approximate with an ABC posterior. Okay, and in our article, we used a very basic ABC approach, the basic acceptance rejection procedure, and in particular an algorithm which is sometimes called reference table acceptance rejection ABC in the literature. And just to recall it, we will briefly go through it. So we observe data Y, and then in the end, as an output, we get samples from the ABC posterior. In the very beginning, we calculate summaries of the observed data Y, and we have to choose a prior distribution. And then n times we repeat the following, and n can be very large. So we draw a parameter value theta from the prior. We use this value to simulate synthetic data from the output process, and then we calculate summaries of this path of this data set, and we calculate the distance to the observed data. We store all the sampled values of theta together with the corresponding distances, and in the end we keep those values of theta as samples from the posterior, which yielded distances smaller than a threshold level epsilon, which we obtain as the pth percentile of calculated distances. Okay, and it is well known that the quality of such an algorithm can highly depend on some important ingredients. And in this talk today, we will focus on answering the following two questions, namely, how should we choose the summaries? And second, how should we actually simulate the data from the model? And in the following, I will try to guide you step by step through the ideas that we had to answer these two questions. Okay, so let us start with the summaries. Like the first challenge we were confronted with is the internal randomness of the SDE. So with that I mean that several paths, even though generated under the same or very similar parameter values, can look very different. And also if you change the parameter theta considerably, it might be difficult to distinguish the paths. I'd like to illustrate this here. So what you see are three realizations of the output process. I hope you can see the colors well. Let's say the blue one is an observed data set, and the gray and red paths are simulated synthetic data sets within the ABC procedure. And I tell you that one of the two is simulated with a parameter value which is very close to the one used for the observed data, and the other one is simulated with quite a different value for theta. And what the ABC algorithm needs to be able to do is to assign a smaller distance to the path that had been simulated with almost the same value of theta. So in other words, it needs to find a useful answer to the question, which distance is smaller, the one between the blue and the red, or the one between the blue and the gray curve? And probably you agree with me that by looking at this type of data, it's very hard to answer this question. So the idea that we had is instead of working directly with the paths of the output process, to make use of the property of the model that there is some underlying invariant distribution, and to map this data to its invariant density and invariant spectral density. So the latter one is the Fourier transformation of the autocovariance function, and it allows you to change from time to frequency domain. Okay, but so how should we understand this setting? So I try to explain again. So imagine you have a realization, a path y theta from the output process, then what we do is to take this data set and we use it to estimate the invariant density of the model by using a standard kernel density estimator. And we use it to estimate the invariant spectral density of the model by using a standard smoothed periodogram estimator. And I will show you what happens when we do this. So we take the data and map it like from the bottom panel to what you see, from the top panel to what you see in the bottom panels, to the density and spectral density. And ask again which distance is smaller, then and provided that you can see the colors well, I think this question is now very straightforward and easy to answer, because the blue and the red curves are now almost overlapping, while the gray one is clearly deviating. Okay, and indeed, so the parameter value I used to generate the blue observed path was 135. The red path was drawn under a very close value, and for the gray curve we used 139, which is already more far away. Okay, so in some sense, by doing this kind of data mapping, what happens is that the data gets less sensitive to the intrinsic stochasticity of the model. Also because both the density and the spectral density are deterministic functions of the parameters. And only data sets which were generated under the same or very similar values of theta are mapped to almost the same objects. And also these objects react very sensitive to changes in theta. And another thing we observed in our experiments is that starting from here, it does not matter so much anymore which kind of distance you choose between these curves. It does not strongly influence the ABC results. So in the end, we decided to simply compute the area between the densities and between the spectral densities, and basically to sum them up. Okay, and let me just say a few words why we consider both types of densities. The drawback of the invariant density is that it does not take into account the structure, the dynamics of the path. So for example, if you would shuffle the data set, you would end up with the same density. And in contrast, the spectral density takes into account the dynamics. For example, mainly the frequency and so on. But a drawback of the spectral density is that it does not take into account the mean, or if you want, the position of the data sets, while this is done with the density. And we observe that when using both, we end up with quite promising results. Okay, but let me now recall this a bit and also mention a few words about the final distance that we used within the ABC algorithm. So again, we have an observed data set Y and a synthetic data set Y theta. Then as a summary, we calculate both the density and the spectral density of Y and of Y theta, and then as an ABC distance, we basically take the sum of the areas between the spectral densities and the densities, and with area we actually mean the integrated absolute error, which is defined as you can see here, and we approximated it using trapezoidal integration. And we have to consider a weighted sum of these quantities such that both areas are kind of the same order of magnitude. And this is particularly needed because the spectral density does not integrate to 1. But I don't like to say too many words about the weight. I'd like to just mention that we obtained it by doing an ABC pilot simulation. And for further details, I'd like to refer to the article. Okay, so let us recall what we have and take a look again at the algorithm. I also want to do this to mention a further detail for completeness, because in our experiments we actually observed M datasets corresponding to M paths of the output process. And we computed in the beginning the summaries, so the density and spectral density of all the M observed paths. And then within the ABC procedure, we compute the distance to all of them and then finally return the median as a global distance. Okay, but that's just a detail, and I'd now like to finish the discussion about the summaries and the distance, and we will go ahead by answering the second question: how should we actually simulate synthetic data from the model? Okay, so I can see that someone raised hand.
Yes, Gail, do you have a question? Please go ahead.
Yes.
I think that's not your usual voice, Gail.
Yes.
Can you perhaps post the question in the chat? I think the audio is somehow distorted. Okay, there might be a technical glitch, so maybe let's just continue. Yeah, and then we have the questions at the end.
Gail was writing in the chat, keep going, so we might try to get in contact with her later.
Okay.
Yes.
So,
okay.
please go ahead. Thanks.
Okay, thanks. So probably we can try to get back to the question later in the end. Okay, so we are coming to the second question, which is how should we actually simulate data from the model? And well, the very first thing we have to do when we simulate from an SDE is that we have to consider a discretized time interval. So we will actually simulate the process at discrete time points Ti, and we consider equidistant time steps delta between these discrete points. And then basically there can be two situations. The first one, and this is very rarely the case, is that we can have exact simulation of the process at these discrete time points Ti. It means the data that we simulate really corresponds to realizations of the output process. It also means we do not introduce a further level of approximation, and we still sample from our ABC posterior. And so basically, this will be possible when we can derive an explicit solution of the SDE. But, and this will usually be the case, that we need a numerical method to approximate the process at the discrete points in time. So the resulting data is denoted with a tilde. And in this case, we introduce a further level of approximation into the ABC procedure. And this is indicated by denoting the posterior with an ABC num. And when we are in this situation, we have to be a bit careful, because we defined our summaries based on the invariant distribution of the model. So the algorithm can only yield successful inference when this property is preserved in the huge amount of data that we simulate from the model. Or in other words, what I want to say is that there exist measure preserving numerical methods which give you the correct behavior of the model, and there are non-preserving ones which may lead to the wrong structure or to the wrong behavior of the model. And unfortunately, standard numerical methods such as Euler-Maruyama are among the non-preserving ones. So for example, what Euler-Maruyama tends to do is to overestimate the second moment of oscillatory models, resulting in data sets with larger amplitudes. So I'd like to illustrate this here, where you have a blue path, which is as the path should look, and a red one produced with Euler-Maruyama, which is of larger second moment. And when this is the case, then the invariant density and spectral density are not preserved, and the algorithm cannot yield to successful inference. And this issue I'd like to illustrate in the following. So I'd like to show how this fact can influence ABC results. So we will do this by looking at the toy model, and we will have a look at the ABC algorithm when we apply exact simulation of the data, measure preserving data simulation, and a non-preserving Euler-Maruyama method. Okay, so the model is the damped stochastic oscillator. It can be written, or it is a linear SDE, which means that we can solve it explicitly, and this is the reason why we have exact simulation available. Then the model has three parameters that we wish to infer. We assume that the process is observed through its first coordinate. And yes, so first, let's apply the ABC algorithm to this model under the optimal condition of exact data generation. And here you see some results. So we start with uniform prior distributions. Then we use simulated data as the observed reference data, because then we know the true values, which are marked as black vertical lines. And the blue curves are the marginal ABC posterior densities. And we see that they have a nice unimodal shape and a center around the true parameter values. And now let me show you what happens when we replace exact synthetic data simulation with a measure preserving numerical method. I will come back to this method later. So we see that we get basically the same marginal posterior densities, which are marked here as dashed orange lines. And now we may ask what happens when we wish to use Euler-Maruyama for synthetic data simulation. And I hope this will not shock the audience too much, but in this setting, sorry, I have problems. In this setting, Euler-Maruyama is not even applicable. It means it's not applicable for the chosen time step, which is 10 to the power of -2 here, because it produces paths with such overestimated second moment that the data is computationally pushed to infinity, and we end up with computer overflows, and we have no chance to derive an ABC posterior. So in order to obtain a comparison with Euler-Maruyama, we have to use an even smaller time step, and we also get back to the simplest task of only inferring one parameter. So we now consider time step delta power -3 in this case, Euler-Maruyama does not yield computer overflows for this model, but we see that it's still not able to reconstruct the desired posterior. You can see this by the dotted line. Okay, so it means that we would have to use an even smaller time step to possibly get better results with Euler-Maruyama. But then the problem is that things are getting highly inefficient. And if you think of the ABC procedure, where you have to simulate a huge amount of paths from the model, it might happen that the algorithm even gets computationally infeasible. Okay, so this means that what we propose to do is whenever you use a numerical method, one should make clear that this method is really doing what we need. And in our case, what we need is that it preserves the underlying invariant distribution. And in particular, we are looking at so-called splitting methods. And these methods I'd like to introduce in the following. Okay, so I will illustrate this method on the neural mass model, but again, it can be directly applied to other models of similar type. And I'd like to refer to the article that is shown on the slide. In this article, the authors give a formal proof that the splitting method does preserve the underlying invariant distribution. Okay, but for now, I'd like to give you the basic idea of this method, and I'd also like to show you how you can implement it. Okay, so if we look at the SDE, we see that the only nonlinear term, I'm sorry, sometimes the slides jump around. Okay, you see that the only nonlinear term is the function g, which depends on the component q, while the rest is linear. So linear SDEs could be solved explicitly, but nonlinear ones are not solvable. So the idea is actually very simple. The idea is just to split apart the nonlinear term such that you end up with two equations. One is a linear SDE, and the other one is a nonlinear but very simple ODE. And both can now be solved explicitly because the linear SDE can be written as you can see on the slide, and standard SDE theory tells you that in a discretized regime, when you have a time point xti, you get to the next point xti plus 1 by multiplying with the matrix exponential, plus adding some noise, and noise is are Gaussian vectors with null mean, and with a covariance matrix that can be obtained as a solution of the matrix valued ODE, which is written here. Okay, and the second one is nonlinear, but the simple ODE. We see that the first component does not change in time. And for the second one on the left side, we have p, while on the right side, the function only depends on q. So its function is just a linear function. And we know how to get exact paths. Okay, so both are solved explicitly. And then the next task is to find a proper composition, so to compose them in every iteration step. And it turns out that a composition named after Strang does very well. So it has been observed in the literature, and this one I'd like to show you. So the question is given a data point xti, how do you obtain the next one? And you can do it in 3 steps. So you take xti, which is given as a starting value of the ODE, that you solve with a delta half step. You take what you get as a starting value for the SDE that you solve with a delta step, and you take again what you get as a starting value for the ODE that you solve with a delta half step. And you could also think of these steps as written down in one line, and then this would replace, for example, one step of Euler-Maruyama discretization. Okay, so and now we have everything needed for our algorithm. So we can now finally apply it to the neural mass model. But again, before we do that, let us briefly recall the algorithm. So the algorithm will now get us samples from a posterior that we call pi ABC num, and the num stands for the fact that we can only derive approximated data that we denote by y theta tilde, and this data we obtain with a measure preserving splitting method. And this method guarantees that the summaries, the density and the spectral density are well preserved. Okay, but now let's apply this algorithm to the neural mass model. Remember, there were three parameters that we wished to infer, sigma, mu, and c. Again, we start with uniform prior distributions. We use simulated data as observed reference data, such that we know the values, which are again marked as black vertical lines. And the blue curves are the marginal posterior densities. And again, we get the nice unimodal shape. Okay, and then I'd like to show you once again what would happen if under the very same setting we use Euler-Maruyama instead of the splitting method for synthetic data simulation. And what you get are marginal posteriors which can be far off from the true values. And probably this gets even clearer by looking at another comparison that I'd like to show you here. So you see the big black dot corresponds to the true parameter vector for C mu and sigma. And the green dots are the kept posterior samples under the splitting method. They are nicely spread out around the true parameter value, while the red dots, they correspond to the kept samples under Euler-Maruyama, and they can be, or they are far off from the true value. Okay, and then finally, we also applied the algorithm to real EEG data of such type. And what we get are again, so we see that the uniform prior distribution again nicely updates to unimodal shaped posterior densities. And this is basically what we were hoping for. Okay, so I'm approaching an end. As a very last thing, I'd like to show you the 95% credible bands of trajectories, density, and spectral density that we obtained by plugging each of the, in this case, 1,000 kept samples into the model and producing paths always under the same random numbers. We see that the bands are tight, so it means that indeed all the kept samples lead to paths of the same behavior. And moreover, in the third panel, you see a zoom of 1 second. And here you see that we were able to reconstruct the oscillatory, the algorithmic frequency behavior of the EEG data, which is around 10 Hertz. Okay, good. And then I'm already coming to some conclusions. So the proposed ABC approach, what we observed is that it only yields successful inference when combining in the measure-based summaries with a measure-preserving numerical method. So this could also mean that probably sometimes it is better, instead of considering summaries and the numerical method as very separate issues, it can be helpful to discuss them together. And in contrast, we observe that the inference returned using Euler-Maruyama can lead to very wrong results. And as I mentioned earlier, one may obtain improved results for small enough time steps. But first, things are getting computationally very heavy. Second, it's not so clear what small enough actually means. And third, even for very small time steps, you never have a guarantee that Euler-Maruyama preserves the invariant distribution. And in contrast, for the splitting method, there are formal proofs which tell you that this method does what it should. And then as a last point, what I'd like to mention is that we used a very basic acceptance rejection procedure to illustrate that even in the basic framework, the discussed ingredients may yield very promising results. But what we believe is that these ingredients can be also used in more advanced algorithms. Okay, and yes, with that, I'd like to finish my talk. I'd like to thank everyone for still being around, and thanks a lot for your interest.
Okay, thank you, Irene, for your talk. There has been a couple of questions before during the talk.
Okay.
Maybe Gael, who had the first question, can try to phrase it again, hoping that now the mic is working better.
Can you hear me now?
Yes, I can hear you.
Okay, all right. Thank you. That was really interesting. Thank you very much. My question really was all about the choice of summaries, which in my experience with these latent variable models generally defined is critical and difficult. And I wondered whether your focus on the invariant distribution of the observed variable as your summary measure essentially would be informative about parameters that are really linked to the intrinsic randomness of the data. So in other words, something like the variance of the latent process, or indeed the degree of autocorrelation in the latent process, if you've got that sort of process happening here. Would information about those sorts of parameters be lost by looking at a summary measure that's just looking at the invariant distribution of the observed?
No, I think it's actually quite well captured in both the density and the spectral density, because especially if you have a parameter like influencing the variance or similar, then it's very clearly visible, for example, already in the density. And I can imagine that such a parameter also might have a strong influence on frequency behavior of the data, which would then also be clearly visible in the spectral density.
Have you compared, say, in a simple version of your model, your ABC-based posteriors with exact posteriors? Have you been able to do that? Because that's really the test, isn't it? Yeah, that's when you'd know.
That's, of course, a very important and interesting point, but I have to say that in this article, we don't have a comparison with the true posterior, because the setting is just too complex and everything. So,
may I add two points?
Of course.
Okay. So one thing is that the problem is that having not available the likelihood, we do not really know how to derive the true ABC posterior. But what you were saying is exactly what happens in one of the examples that Irene was showing. So I'm trying, I don't know, Irene, can you point that? Okay, so for example, if you look at this example, if you look at this model, you see that sigma is entering the second coordinate that is not observed.
Yeah.
But when we perform ABC inference, we actually estimate it because the model is hyperelliptic, so it propagates also to the first coordinate. So this is an example that is exactly what you are saying. Sigma is the parameter that is playing a crucial role in the latent variable, but due to the structure of the model, it also propagates to the first coordinate that is the one observed. So when we estimate the invariant density and invariant spectral density, so the autocorrelation of the observed coordinate, we are able also to estimate the sigma parameter entering in the latent coordinate. And if you see here, actually, that would be an example. We are actually undergoing a study on this where we also succeed in writing a sort of pseudo likelihood. So we should be able to compare our ABC approach with the, let's say, full or the true ABC posterior under some pseudo likelihood derived. So hopefully there will be more coming at some point.
Okay, thank you. Great.
Irene, if you look at the chat, there was also a question from Umberto. I don't know whether Umberto wants to post it or.
Okay, I cannot really see all the messages, so please just ask.
Maybe it's more fun if I ask. So, on slide 31, you were just comparing the posterior, using the Euler-Maruyama non-preserving method, and with the numeric method based on the measure preserving approach.
Yes.
But with Euler-Maruyama, I would just wonder if the comparison is fair in terms of the epsilon that you chose, because this with Euler-Maruyama you chose the first percentile, and previously you had the 0.05 percentile. So
the percentile is larger in this case because here we only inferred one parameter, so we did not need to simulate so much data. So n is only 10 power 5, and it means in this case we keep 1,000 posterior samples. And also here we keep 1,000 posterior samples. So the number of kept samples is the same in both settings.
Okay, so the comparison is based on computational effort rather than value of the threshold.
Yes, so the threshold was not so much on the focus. It's
but I'm fine. Great.
Okay.
But here in this figure, what is the epsilon that you chose for the measure preserving ABC?
You mean the time step delta?
No, epsilon.
The same.
Yeah, so I mean here epsilon is the same for both the measure preserving and Euler.
Yeah.
I think that this was the question of Umberto.
Okay, I see. Yeah, of course it's the same. So we keep the same samples for all the so the same number of samples for all the posteriors that are shown here. So from this perspective, it should be a fair comparison.
Yeah. It was not clear to me that the epsilon was also exactly the same between the two comparisons. But if you say so, that's great. Yes. And even if they were different, I understand that you're comparing posterior based on how much effort it takes to produce the n paths. Anyway, it's fine.
Okay, thanks.
Yeah.
Okay, there was one more question from Frank.
Yes. First of all, thanks for the nice talk. I was wondering, in the Jensen-Reed model, there are many parameters in there, and you chose 3 of them. So why did you choose these 3 And also, I saw in the paper that 2 of the diffusivity constants are very small. So I guess they should just be 0, or?
Yes, okay, so it's true that there are, I think, a bit more than 10 parameters in the end. But so first of all, not all of them, so some of them were introduced only, let's say, for mathematical convenience, and not all of them are relevant from a biological perspective. So for example, the noise matrix contains sigma 1, sigma 2, sigma 3, so we need 3 of them. And this is needed, for example, to prove that there is the underlying invariant distribution in this article you have on the slide, but actually only the second sigma is interesting from a modeling point of view. So this is why we reduced everything down to 1 sigma, which was among the 3 parameters we were interested in. And the parameter C, I mentioned the internal coupling parameter. This is kind of the most impressive one, because this is the one which really allows you to change from like algorithmic behavior to very fast spiking behavior and so on. So this one we definitely wanted to have. And also many of the parameters are very well reported already in the literature, and many values are well known, while the parameter mu and sigma, have never been studied or estimated before, because they are new in an SDE reformulation of the model, because the original one is actually an ODE. Okay, so we have the 3, and
yeah, I'm not entirely sure, because even if you read in their original paper, yeah, there are some settings which seem to go back to this paper from the 90s, and I think this is from maybe experiments even with animals, and I don't think there has been any checkup on that later. So that's why I'm asking that I'm not, and also I saw a few different papers because I got interested in this model, and it was not entirely, I think they don't give a sort of, they don't agree with the message on which parameters are supposed to be known or not. So that's why I'm asking, and but I understand the motivation that you took here.
Yeah, I mean, what I should also mention is that we definitely tried to estimate more of them, but there are also identifiability issues. This is, if you're interested, more detailed, explained in the article. I did not mention it. The problem with the model is that sometimes different combinations of the parameters yield to the same type of paths, so the same type of output behavior. And in this case, I mean, at least with our algorithm, we have no chance to identify all of them. And we even were able to identify some regions of these parameters where they give the same type of behavior. So this model is quite tough because there are some identifiability issues.
Okay, thanks.
Okay, you're welcome.
There was one more question before from Moritz, but I don't know whether it's answered.
Yeah.
Yeah. Yeah, thank you for the talk. I was just curious. So the stationary distribution shows the difference between different choices of discretization scheme in the strongest way. I can see that. I was curious how strong this is. So how sensitive is the second metric you use, the spectrogram, to the choice of the integration scheme?
It's like I think I had one slide, so it's also very sensitive because like the spectral density, let's say basically it carries information about both frequency and amplitude. And I mentioned that Euler-Maruyama in oscillatory models often has problems with the second moment, in other words, with the amplitude. So it's definitely affecting a lot the spectral density. And you can see it on this slide, where the blue curve is how it should look, and the red one is what you actually get.
Okay, I see. Thank you.
You're welcome. Massi?
Yeah, just to say that there is more. I think that there is more time for a question. So, Dennis, if you want, you are more than welcome to pose your question.
Okay, thank you, Massi. Thanks for the very interesting, nice talk. My question is, how easy would it be to generalize the summaries that you have to a case where you've got multiple observed time series?
Yes, that's also a good point. So the reason why we looked at a one-dimensional output process is because we had the feeling that this is actually the most challenging situation. But we believe that it could be straightforwardly extended to multiple observations. Then you could just calculate the distance that I showed you for all the components. And for example, return a global distance by just taking the sum. And we even think that results may improve by taking into account cross-spectral densities in such a situation.
Okay, thank you.
You're welcome.
So yeah, actually this is what Irene is planning to do soon on a set of EEG data. So instead of observing only one EEG time series, you have several of them. So you want to also reconstruct the underlying dependence mapping. So the cross covariance will play a role in that direction. Okay, there is Mikael having a question.
Yes, hi. I have a quick question for the end where you show the predictive sample passes.
In the end?
Towards the end of the slide.
Yes,
if I understood correctly, it was like posterior predictive samples. Here, oops. One more, okay. This one here. It's just like you took samples from the posterior and then you passed them through the model, and you show the variability that we get in Y theta, like in here in the top row.
Exactly.
Okay, so in the very beginning of the talk, you motivated the talk while saying that even a tiny change in the parameter yields really, really different time series. But here it seems that actually there is if you take samples from the posterior, that actually there is very small change in Y theta. So there is very little variability, like what we can see here. Can you explain how these two things go together?
Yeah, I think in the beginning it was simply a larger change.
I think it was like from like a 0.1 change, wasn't it?
No, it was, so the 0.1 was the one which was actually very close and where we got almost the same curves, while the change appeared when I chose 139, which is already larger. And I think it was just a bigger change in the beginning as we have here.
Okay.
But Irene, aren't these lines the first that you see on top related to not the real trajectory, but like the median observed?
Yeah, right. So here, for example, right. So this was my point where I think in this slide, wasn't it the one of the curves was very like Okay, here, all right, so you say the gray one is we just 105.1, but it's very different from the blue one, right? So what I don't quite get is like if you just change theta observed to 135 to 135.1, you get instead of the blue trajectory, the gray ones. But at the very end,
okay,
we get this this kind of graphs that, you know, when you, I guess the posterior is a bit broader than just like has more variability in there than just the 0.1 change. So I don't quite understand how these two things go together. Did you fix here like a random seed or something?
Exactly, now I got it. So the difference is that in the beginning, where the paths were very different, we used different random numbers, so different seeds. While here, all so in this slide, all the paths are obtained under the same seed.
Okay, so it's not really a posterior predictive samples, but somehow showing something else, really.
Yeah, it's to understand whether the kept samples really give us paths of similar type of behavior.
If you know the source of randomness, in a way, if you keep that constant.
Exactly.
Okay, got it. Thanks.
Okay, I don't see any further questions, so I would like to thank Irene again, and thank you all for being here. And we will see you in 2 weeks with the next speaker. Thank you, Irene.
Thanks a lot.